Hello and welcome to a new video. In today's video, we'll be discussing about Cascade and Cascode amplifiers. So before we begin, let's revise some of the concepts from the last few videos. We'll look at a few design examples and try and understand how to analyze those circuits. We'll then look at why do we need to cascade stages to begin with, and then look at some examples of cascaded stages, and then look at one particular cascaded stage. Cascaded stage basically means where you connect multiple stages one after the other. So we'll look at a specific cascade which is known as the cascode, which consists of a common gate that follows a common source stage. So let's first begin by revising what we've done previously. So here's a circuit given to you and you want to identify the small signal gain of the amplifier. So whenever you look at circuits like this, it is first imperative to understand what the circuit is doing. So the first thing you want to identify is what kind of a stage does the circuit look like. Now once you identify the kind of stage the circuit looks like, then it becomes relatively easy to then write the gain, because then you kind of know the formula or the format in which the small signal gain should be expressed in. So now if I look at this particular circuit, first thing you see is that the input signal is given to a gate. Therefore, this has to be either a common source or a common drain configuration. Secondly, in this case, you see that the input is given to the gate of the PMOS, where the source of the PMOS is connected to VDD, in which case the source is grounded for AC signal. And there are a bunch of transistors that are connected to the drain of M1. So if I were to think about this amplifier stage, this looks like a common source amplifier built using the M1 PMOS. If I want to identify what M1 is doing, M1 is the transistor that is actually converting this input voltage to a current, right? So this is your transconducting transistor M1, which means the gain is going to be written in some format GM1 times the load that is connected to the output, right? So in the case of a simple common source amplifier, this was minus GM into RO parallel RL. So here we need to identify what is the net output resistance in small signal that is connected to this transconducting amplifier. And so therefore, as I mentioned, the effective transconductance of the circuit is GM1. If I look at the total load now, that is, I'm going to be standing at the output node. And so I have two components of the load, if you will. One is of the load that I can see when I look into the drain of M1. And the other load which I see when I look into these two nodes towards the AC ground, right? So let's identify the two loads. When I look up into the drain of M1, I see is the drain of M1 being shorted, and so here the resistance that I see looking up towards VDD from this output node is RO1. Now when I look down from this output node, I see two components. I am looking first into the drain of M2. So when I'm looking into the drain of M2, the resistance I'm going to see is RO2. However, here what I see is, I see this is a PMOS transistor whose gate and drain are shorted. So therefore, if I'm looking into the source of this PMOS transistor, I'm going to get a resistance that is going to be given by 1 by GM2, a GM3 parallel RO3. This should read GM3, right? So therefore, your down resistance is RO2 parallel with RO3 parallel 1 by GM3. Again, this should read 1 by GM3. And so therefore, now if I calculate the gain of this circuit, it's going to be minus GM1. Remember, it's a common source amplifier. So it's minus GM1 into RO1 parallel RO2 parallel RO3 parallel 1 by GM3. Again, this should read 1 by GM3. Okay. Let's look at another example. Okay. So here again, I want to find out the small signal gain of the circuit. So as always, let's first begin by identifying what is the kind of amplifier stage this circuit looks like. So again here I have an input voltage in giving into the gate of a PMOS transistor. So therefore this has to be either a common source or a common drain configuration. Now if you look at this M1, which is your transconducting transistor, it has M3 connected to its source, and the output of this amplifier is pulled from the drain of M1. So if I look at M1, which is doing the transconductance, I'm applying a signal between the gate and source, and I'm pulling the output between the drain and source. So this configuration looks like a common source configuration. However, you see that the source of M1 is not grounded, but it's actually connected to a transistor. Now this transistor is going to provide some sort of a degradation resistance or a source degradation. So what you have essentially here is a common source stage with source degradation. So that is the kind of amplifier. So again here we know how the gain of this has to be. Again, given that lambda is equal to 0, this is going to be of the format GMRD by 1 plus GMRS. So we need to identify what is the equivalent RD, what is the equivalent RS, and then we'd be able to write the expression for the same. So the drain resistance, so whatever is connected, this RD is going to be whatever is connected to the top of Vout. So in this case, I'm looking into the drain of M2. So the drain resistance, or the RD if you will, equivalent RD of the circuit is going to be RO2. Similarly, if I'm sitting at the source of the transconducting transistor, I'm looking down at the source degradation resistance. I'm looking down into M3, which is a diode connected transistor, right? So the drain and the gate of the transistor are shorted. So I'm looking into such a diode connected transistor. The source resistance is going to be 1 by GM3 parallel RO3. So that's the resistance I'm connected to the source. RO2 is connected to the drain. The effective transconductance, or the transistor that's doing the work in the circuit, is going to be M1, and so its effective transconductance is going to be GM1, and hence I can write the gain as minus GM1 into RO2, so that is GMRD format, divided by 1 plus GM1 into RS, in this case is going to be RO3 parallel 1 by GM3. So this is basically, you can decompose the circuit down to a common source stage with source degradation and then quickly get to its small signal expression. Now let's look at another circuit here. So here again, as always, let's first identify what is the stage this resembles. So again, I have a circuit where I have a transistor. The input signal is applied at the gate of the transistor. The output signal is pulled from the drain of the transistor. So this has to be a common source amplifier. Now what is happening here is that this entire circuit here is working as the load connected to transistor M2. So again, you see this kind of an amplifier is a common source amplifier. M2 is doing the transconductance. So the gain of the circuit is of the format minus GM2 into RO2 parallel RD. So we need to find the effective output resistance. So looking into the drain of M2, I'm going to get an RO2. Looking down, I'm going to get what? Looking down, what do I see? Looking down, I see this RS, which is a resistor connected in series with a transistor M1, which is biased in saturation, right? So what I'm doing here is, if I'm at the output node, I'm looking at RS through M1, right? So I'm looking at RS through the drain source path of M1, and we've looked in the previous videos that this RS therefore gets morphed into a larger resistance whose value can be roughly written as GM1 into RO1 into RS. So if I'm looking down, it's RS. If I'm looking from the drain of this M1, I'm going to get GM1 RO1 RS. Right? So therefore the net resistance I have is RO2 parallel GM1 RO1 RS. And so my net gain of the circuit is going to be minus GM2 into RO2 parallel GM1 RO1 RS. Okay. Alright, now let's look at another circuit here. So again here you're asked to find what is the gain of this circuit. So first thing first here is this circuit is slightly different from the previous cases here, because you see that while I'm giving the input to a transistor M1 here, I'm not collecting the output from any of the other nodes of M1. So this essentially tells you that this is not a single amplifier stage, but consists of more than one amplifier stage, right? So what you see here is the output of the circuit is being collected from the drain of M2, whereas the input is applied to the gate of M1, right? So therefore what you see here is that you cannot think of this purely as a single stage, rather than I have two stages. And how do I identify the two stages? I have this one stage which is made up of M1 and I1, and this is a common drain or source follower, because here I have an input connected to the gate and I'm pulling the output at the source of M1. Now this output, which is the source of M1, then is fed as an input of a second stage which consists of M2 and RD. Now in this case I'm giving the input at the source of M2 and pulling the output at the drain of M2. So this M2 is connected in a common gate configuration. So what I have here is I have a source follower and a common gate that follows the source follower through this node here, right? So therefore I have two stages here. So what I need to first find out is the gain from the individual stages, from their inputs to their outputs, and then ensure what the R and R outs are to find the actual gain of the circuit. So let's call this intermediate node Vx. So now from Vin to Vx, this is an ideal source follower. Lambda is equal to 0, which means Ro is infinity. So in the source follower, the gain is given by GMRO by 1 plus GMRO. If Ro is infinity, then the gain of the ideal source follower is 1. Therefore, that means that Vx follows Vin, right? So the gain from Vx to Vin is 1. And if you look at the output resistance of the source follower, the output resistance of the source follower is given by looking into the source of M1, or looking into the source of M1, which should be 1 by GM1. Again, they should read 1 by GM1, right? Now if I look at this second output, so now this Vx forms the input to the common gate stage. And so again here, because lambda is equal to 0, the gain for the common gate stage is simply GM2RD, right? So V out by Vc is plus GM2RD. Now again, this is a common gate configuration, so it has a finite input resistance because the input is given to the source and it's given by 1 by GM2. The output resistance of the common gate is going to be given by RD, right? So what you see here is you have two amplifiers connected one behind one another. But because the RO of the first stage is not 0, and because the Rn of the second stage is not infinity, only a part of the output is going to be used as the effective input of the second stage, right? And that's because input resistance of the common gate is not infinity. So what I have is the output resistance of the first stage is 1 by GM1. The input resistance of the second stage is 1 by GM2. So only 1 by GM2 divided by 1 by GM2 plus 1 by GM1, that is the effective input voltage that this common gate sees, is going to be whatever is the voltage that falls through the resistor division that occurs between 1 by GM2 and 1 by GM1. And so therefore your AV is going to be given by 1, that is the gain of the first stage, times this resistive division parameter, which is 1 by GM2 divided by 1 by GM2 plus 1 by GM1. And this is coming because 1 by GM2 is the input resistance of the second stage, and 1 by GM1 is the output resistance of the first stage. That times the voltage gain of the second stage. And so the effective small signal gain therefore is going to be GM1 GM2 RD divided by GM1 plus GM2. So again, please keep in mind that for a question like this, it's tricky, and the answer would be wrong if you had assumed that the Rn of the second stage was infinite, right? So please remember that when you break these circuits up into stages, make sure you know what the right Rn and what the right R out of these various stages are. Okay, now let's look at a design problem. So I've been given a circuit here. So I've said design a source follower for a current of zero point 0.8 milliamps. What that means is that M1 is biased at a DC current of zero point 0.8 milliamps and for a voltage gain of zero point 0.8 volt per volt. Assume UNCOX, VTH, lambda 0, VDD is 1.8 and RG is 70 kilo ohms. So in a problem like this, first you need to ascertain what is it that you're asked to calculate for. Right? So in this case, you're asked to design a source follower, which means that you need to find one, the size of this transistor M1. You'll also have to find the value of RS, if you will. Right? Now, let's start doing that. So we need to estimate the value of RS here, and we need to find the size of M1. Now we know that ID is going to be flowing. So the bias current ID is going to flow through M1. That's going to be the same current that's going to be flowing through RS, right? And even though there's an RG connected between the gate and drain of the transistor, there is no current that flows to RG, right? So the voltage at the gate, the DC voltage at the gate is going to be the same as VDD because I is equal to 0, which means these 2 points are at the same potential. So even though I've not explicitly given what the overdrive voltage is, you know what the voltage at the gate pin is, right? So again, this is information which you can extract based on how the circuit works. And you need that because then you can use this information to go ahead and find the values. Right? The first thing is you know that this looks like a source follower, and for a source follower with lambda is equal to 0, R naught is infinity, so I can write this gain from V in to V out as GM1RS divided by 1 plus GM1RS, and that should be 0.8 volt per volt, right? And if I write GM1, let's assume that I have a DC current of ID that flows through the transistor, then 2ID by VOV is GM1. So I have 2ID by VOV into RS divided by 1 plus 2ID by VOV into RS should be 0.8. Or I have a relationship between IDRS and VOV. 2IDRS divided by VOV plus 2IDRS should be 0.8. Now, what is VOV? VOV is the overdrive of M1. The overdrive of M1 is given by VGS minus VTH, right? Then the VGS of M1 is given by VDD minus IDRS. Remember, this pin is at VDD. IDRS is the voltage that's going to be dropped across RS. So the source of M1 is going to be sitting at IDRS. So VGS is going to be VDD minus IDRS. I remove a VTH from that and that's going to give me my overdrive voltage. So my VOV is given by VDD minus VTH minus IDRS should be 0.8. Right, so now I have an equation here where all the parameters in this are known. ID is known, VDD is known, VTH is known. Right, so only thing unknown in this is RS. So I can solve for RS and I get RS to be 583.33 ohms. Right? So this is the resistance that needs to be connected to the source of M1 so that I can have a current of 0.8 milliamp flowing through the circuit and have a small signal gain of 0.8 volts per volt. Now all I need to do is find the size of M1. So to find the size, if you think about M1, I know that's VOV, right? And I know it's ID. So from that I can find its size. And so VOV is nothing but VDD minus IDRS minus VTH, which is 0.9336 volts, from which, and I know half mu NCOX into W by L, VOV squared should be ID. So knowing these two, I can calculate the value of W by L to be 61.22. Right? So that's how you solve. Again, key to solving all these circuits is to first identify what are the parameters that need to be solved for, and then make sure you identify all the relationships that you can looking at the circuit in front of you. So let's look at another example. So here you're asked to design a common gate stage for a gain of 4. Our signal is 0. What our signal means is essentially the signal source that is connected to the input voltage doesn't have any input resistance, so direct voltage is connected here. R3 is given to be 500 ohms. 1 by Gm of this transistor is given to be 50 ohms. And the power budget of the circuit is given, and it's given to be 2 milliwatts. You're also given VDD, VTH, and mu and Cox. So again, first thing is you have to figure out what you need to find out. So you need to basically find the values of R1, R2, RD, and the size of transistor M1, right? So let's first begin with that. So first thing is we know lambda is 0. This is a common gate stage, and therefore the gain of the common gate stage from input to output is very simply GM RD, right? And that is because there is no signal resistance. And so therefore I can write my RD as AV divided by GM, which in this case would be 200 ohms. So the first thing is I've calculated what the value of RD is. Now I need to find the current. So I know the power budget. Now remember, the current is going to flow in two paths. There are two paths between VDD and ground. First one is the path through RD, M1 and R3. The second is the DC path between R1 and R2. Remember, R1 and R2 have a path to ground. So there are two current paths that flow through the circuit, and this current 2 divided by 1.8 is the total current that flows from VDD, right? So out of this 1.1 milliamp, some of the current is going to flow through the transistor, and some of the current is going to flow through the resistive bridge to create the gate voltage. Now how you divide this is up to you. So just for illustrations, what we can do is we can budget a milliampere for the amplifier and only about 0.11 milliampere for the resistive bridge, right? So how do you decide how much of that is important or which one? So remember, this current, the larger you pass the DC current through the transistor, the higher GM you're going to get, right? So the more current, if you want to use the amplifier, you want to use a smaller transistor. So which means that you want to ensure that you can get the maximum juice out of the transistor, which means you want to get as much as a current, DC current, to flow through the transistor doing the work so that you can get its higher GM. The problem with keeping this current too small sometimes is, if you make this current too small, that's going to require your resistances to become very, very large. Again, which can take a lot of area, which can have a lot of variation to temperature, etc. So this division between, what constitutes the actual workable current versus what is the current required for biasing is something that you need to try, and you need to be based on other factors which are not part of the problem. So hence in this case we will use a budgeting which we deem is a sensible trade-off, right? But if you want to go more accurate, you need more information to figure out how much of the budget should I actually use for the transistor versus what is required if I want to reduce area, reduce power, etc. So if I use the current 1 milliamp in this transistor and 0.11 in the remaining, so now I know 1 GM of this transistor, and if I know the ID of this transistor, then I essentially know VOV, because GM is 2ID by VOV, and so therefore from that I get my VOV of M1 to be 0.1 volts. Now once I know the VOV of M1 to be 0.1 volts, I know the current is 1 milliampere. So using the DC current relationship, I can establish the value or the size of M1 to be 1667.67. So that's the size of M1. Now I still need to calculate the gate voltage and R1 and R2. So now remember, what's happening here is that this VOV is being generated because of this resistance bridge that I have here. This resistance bridge dictates the gate voltage at this node. Right? So I'll first find what the gate voltage at the node is going to be, and that's going to be given by ID into R3. That gets us to this node. Then VOV plus VTH, which gets you to this node, right? So I have IDRS plus VTH plus VOV, which gives me my voltage at this node at the gate to be 1.05 volts. So again, now I know this is 1.8, this is 1.05, the current in the bridge is 0.11. So from that I can calculate the values of R2 and R1. And so I get R2 to be 9.45 kilo ohms and R1 to be 6.81 kilo ohms. Again, remember that these numbers will change depending on how you've divided the currents. Alright, so let's talk a little bit about biasing of circuits. So remember that the bias current of the transistor, as I told you, controls both the GM, the R0, the voltage swing, the size, and hence the area of the circuit. So when we do biasing of circuits, we generally don't like voltage biasing. As I told you, resistors are finicky elements. They require a lot of area. They're prone to PVT, process variations, temperature variations. So we want to establish a biasing technique, essentially using currents. And we want these currents to be insensitive to any incoming voltage fluctuation to the chip, any temperature variations, etc. Now, a very useful circuit in this regard is known as the band gap reference circuit. And this band gap reference circuit actually can generate a current that is insensitive to voltage and temperature. And once we generate this current, that current is essentially mirrored, if you will, across circuits to generate bias currents. So I'll upload a very separate video on how to discuss band gap circuits. But let's just assume for now that we have a reference source and we use current biasing for all our circuits. Now let's think about what are all the various wants from an amplifier. So first thing is obviously the small signal gain. We may also sometimes want to use a circuit to transform resistance. That is, we either want the circuit to work like a buffer, so essentially it isolates everything that's connected prior to it. We want to allow for a large voltage swing. There is no real point in having a circuit with a very high small signal gain if I'm not able to get the output node to swing that large to support the small signal gain. So you want a large output voltage swing. Many a times you're dealing with signals over a certain bandwidth, as you want your amplifier to be relatively agnostic for signals within a given band. So we worry about the bandwidth of the amplifier. We talk about the stability. We don't want the amplifier to go out of whack for certain frequencies, for certain phases, for certain bias conditions. And we also want to just think about the noise performance. That is, if there is a certain disturbance that the circuit encounters, the circuit should be able to recover from it. Now, when we look at the simple stages we've seen so far, it's very hard to achieve most of these goals from a single stage, right? And that's why we do many a times when we implement circuits, we do what is known as a cascade of circuits. That is, we connect multiple stages together so that we can achieve some of the wants for our particular design. Now let's look at a very simple case where we want to cascade two common source stages. So here I have one common source stage made of M1, which is biased with some current source of DC current I1 and some resistance RC1, and that is fed into another common source stage. So a single common source stage can be represented in this format. It consists of a certain Rn and a certain Rout and a gain. Now we know that in the case of the transistor in the MOS common source, because the input is connected to the gate, for most mid-band frequencies, the input is essentially an open circuit, which means that your Rn is going to be infinity. The output resistance of the common source is essentially given by R01 parallel RC1. So what you see here is that if you look at the common source, the gain is directly related to the transconductance and the load, and the output resistance is the load. So one way to increase the gain of the circuit is to increase the output resistance, but that would also basically limit the usable voltage gain that you can get from the circuit. Now because Rn is infinity, what happens is whatever is the output that's generated at the output of the first stage, because the input stage has an Rn of infinity, all of that output falls at the input. So perfect transmission takes place from this output to the next output. And so therefore I can write the total gain of such a circuit as AV1 times AV2, and I don't have an Rn Rout factor in between because the Rn of this stage is infinity. And so then the total gain is given by GM1 into GM2 into effective RO1 and effective RO2. And if you look at the output resistance of this combined circuit, because Rn is infinity, the effective output resistance of the circuit is limited by the output resistance of the last stage, which is given by RO2 parallel RC2. So in this case, what's happened is by cascading two common source stages, one after the other, I'm able to get a good gain or a high small signal gain, right? However, I'm still limited by the usability of this gain because of this large output resistance. So what I do is I want to find out, can I add another stage which can transform this output resistance to something smaller. Ideally, I want my Rout to be as small as possible. And we know that the source follower does precisely that. So what we do is we connect the source follower as a third stage to this cascade of CS stages. And this source follower essentially has an Rn of infinity, an Rout of RO3 parallel 1 by GM3, in most cases going to be 1 by GM3, and it has a small gain. So it's not a gain stage, it has a gain close to 1 or a little less than 1. But what it has is this amazing property that its output resistance is very small. Right? So what I would do in this case therefore is if I look at AV1, first stage is given by minus GM1 RO1. Here again I'm assuming these current sources to be ideal. The voltage gain of the second stage is minus GM2 RO2. The third stage has a gain of GM3 RO3 by 1 plus GM3 RO3. Again, this is a number close to 1. And so the total gain of these stages, because Rn is infinity in all three cases, the total gain is given by the product of the individual gains, which is AV1 into AV2 into AV3. And the output resistance, again, because Rn of the stage is infinity, my output resistance is simply given by RO3 parallel 1 by GM3. The input resistance of this combined stages is given by the input resistance of the first stage, which is infinity. Now let's look at a special case of a cascade, which consists of a common source connected to a common gate. So here basically you have these two transistors, M1 and M2. The input is applied to the gate of M1. The drain of M1 is connected to the source of M2, and the output of the second stage is pulled through the drain of M2. So if you look at M1, M1 has a input at the gate between the gate and source. You take its output from its drain. So M1 is connected in a common source fashion. M2 on the other hand, you apply an input to its source and you take an output from its drain. So M2 is connected in a common gate fashion. So here you have a signal path that goes through a common source followed by a common gate configuration. So how do you find the gain of the circuit? So again, like previous, you can always use the Rn Rout conditions and also find the gain. Let's do this the old-fashioned way. Let's do it using the small signal analysis. So what I'll do is I'll replace M1 with its small signal model, M2 with its small signal model, right? And let's calculate V into V out. Now because M2 has a bias voltage at its gate, I've connected it to ground here. And here you see essentially if you look at the circuit below M1, if you look at the ground here, GM1 VGS1 is flowing into ground. The same current has to flow through RO1 again because those are the only two connections to ground. Which means that this GM1 VGS1 current is flowing in this loop, which forces this current to flow within its own loop. Therefore, there is no current that flows between these two loops in small signal. So if you understand that, then analyzing this circuit becomes very easy. Because then my Vx, if I call this intermediate node voltage Vx, Vx upon Vn is minus GM1 R1. And therefore now my VGS2 is nothing but minus Vx, and therefore I can write my GM2 VGS2 plus the current flowing in RO2 is nothing but VO minus Vx by RO2. The sum of those two currents should be 0, or replacing VGS2 with Vx, I get minus GM2 Vx plus V0 minus Vx by R2 is equal to 0, or I get VO by Vx as 1 plus GM2 RO2. And so therefore, knowing Vx by Vn and VO by Vx, I can write my VO by Vn as minus GM1 RO1 into 1 plus GM2 RO2. And here again, if you see, for most usable cases, this GM2 RO2 is a larger number than 1. So I can replace this 1 plus GM2 RO2 simply with the GM2 RO2. And so the gain of the circuit is essentially given by minus GM1 GM2 into RO1 RO2. Right? So that's the gain of the cascode stage, which is nothing but the product of the gains of the internal gain of M1 and the internal gain of M2. Now let's recall ourselves a little bit about the effective transconductance technique. So any MOS circuit, when it has an input and output node, I can write the output by input or the small signal gain of the circuit as GM times R out, where this is an effective transconductance and this is an effective output resistance. The individual GMs are measured using the following technique. So to measure the effective transconductance, you apply a Vin and you short the output, and then you measure the output current. The ratio of the output current to the input voltage is the effective transconductance that this MOS circuit offers to the input voltage. Similarly, to calculate the effective output resistance, you short the input, you apply a voltage at the output, and you measure the output current. R out is given essentially by V out by I out. Right? So any MOS circuit can be analyzed by this technique directly to find the small signal gain. Now if you look at our cascade circuit again, let's see what's happening here. So if you look at transistor M1, when Vin is applied to the gate of M1 converts Vin to a small signal current, which is GM1 Vin. Now this GM1 Vin flows through the drain of M1. Now because M2 is a common gate transistor, it has an ideal current gain, which means that whatever is coming in the source has to flow out from the drain, which means that M1 is pulling GM1 Vin through its drain, and M2 is going to pull that same current through its drain. So what you see here is when you apply the small signal here, the net current that's being pulled out of V out or from that node is GM1 times Vn. Right? So it looks like a common source because the M2 is just doing the unity current gain. Right? So what you see is therefore the effective transconductance. If I just look at the total transconductance current that's flowing at the output node, it resembles that of a common source with its transconductance GM. Therefore, the effective transconductance of the stack is only GM1. What makes the difference, however, is the load. Right? If I look at the load resistance, again, this is an ideal current source, so infinite resistance looking up. If I'm looking down, what I do to find the load resistance is I short the input. So the resistance looking down from the drain of M1 is RO1. But I'm looking at RO1 through the transistor M2 through its drain of M2, and hence it's going to be GM2 into RO2 into RO1. Right? So therefore my net output resistance is GM2 into RO2 into RO1. So this is my effective transconductance, this is my effective load resistance, and hence I get my gain to be GM1 into GM2 into RO2 into RO1. Now, quick drawback with the cascades compared to the small single stage amplifier. So here now I have two transistors which have to remain in saturation, which means therefore that the output node of the stack cannot go less than the sum of the two overdrive voltages. And secondly, remember that we generally tend to neglect this when I'm doing classes here. But what you see is that M2 and M1 will probably sit in the same P well, which means that M2 is going to demonstrate a substrate effect of VT. So that will need to be taken into consideration when you're doing the accurate analysis. VT of M2 is not going to be equal to that of M1, even though they're of the same technologies. It's because of the substrate effect, because of the finite VDS that's going to be building across M1. Now let's look at a circuit. Now that we understand the cascade, let's try and see if we can look at the small signal gain of this particular circuit. So here what do I have? I have 3 transistors connected in series to the output node. So again here this looks like a cascade circuit. The difference being that the cascade had 1 transistor, this has 2 transistors. M2 and M3 are both the common gate configuration. So if you can think of this as M1 as a common source, M2 as a common gate, M3 also as a common gate, right? So what's going to now, if I want to calculate the effective transconductance, right? The effective transconductance of the circuit is still only because of M1, because that's your common source stage. When Vin is applied, it's going to pull a current GM1 Vin. M2 is also going to pull the same current GM1 Vin. And M3 is also going to pull the same current GM1 Vin. Therefore, the effective current that's going to be pulled from the output node is going to be GM1 times Vin, indicating that you have a effective transconductance of GM1. Right? So adding these two transistors hasn't helped much with changing the transconductance. Now let's do the load resistance. To define the effective Rout, if I want to see what's the total resistance looking down. So I know there are 3 transistors connected one on top of the other. So let's start from the outermost transistor. Looking down into the drain of M1, I'm going to see RO1. I'm looking at this through M2. So looking down into the drain of M2, I'm going to see GM2 RO2 into RO1. And hence, therefore, looking down into the drain of M3, I'm going to see GM3 RO3 into GM2 RO2 into RO1. Right? So the effective resistance looking down is going to be approximately GM3 RO3 into GM2 RO2 into RO1. Right? In the previous case, we just had GM2 RO2 RO1 because we just had one transistor on top of the common source transistor. Here, addition of this M3 creates another cascade effect, if you will. So the Rout increases to GM3 RO3 into GM2 RO2 into RO1. And therefore, if you look at a small signal gain, it's going to be minus GM1 into this resistance. So you see that adding this one more cascade transistor helps you get a much larger gain, right? So all of a sudden now your gain has gone up by a factor GM3 into RO3. Now, obviously, we can keep adding more of these transistors and get higher and higher gain. But the biggest drawback of the cascade is that, again, remember, you need to keep these 3 transistors in saturation, which means that this output voltage node here or this node here has to support 3 VOVs. Right? So what you see here is that as you keep adding more of the cascade transistors, your swing at the output reduces. And especially as transistors scale, as technologies scale, you begin to see that the VDD is scaling quite fast. VT isn't scaling fast enough. And so the headroom in technology is reducing, which makes it harder and harder to support these large cascade stages. So you see that in most cases, your cascade is going to be restricted to not more than 2 transistors. That is just a 2-stack cascade, if you will. Now let's look at the small signal gain of this circuit here. First, let's identify this circuit. So here you see there is an input connected to M1 and output is being pulled through the drain of M2. Therefore, we know that M1 and M2 form a cascade connection. What is M3 doing? M3 is the load of the cascade, right? So M3, if you will, is the current source. M3 is providing the bias current, which is being supported by M2 and M1. So if I again want to find the small signal gain, I start with the effective transconductance. Again here it's going to be GM1 because Vn is going to pull a GM1 Vn through the drain of M1, which is going to be pulling the same current through the drain of M2. And so the effective transconductance is GM1. If I want to find the effective R out, I need to break it up into two parts. One looking up into the drain of M3, the other looking down into this cascode stack of M2 and M1. So R up, I'm looking into the drain of M3, so it's RO3. Looking down, I'm going to be looking at RO1 through M2, so it's going to be GM2 RO2 into RO1. So the effective resistance, if you will, at the output node is going to be RO3, again, sorry, this should read RO3 parallel GM2 RO2 RO1. So that's your effective output resistance, and therefore your total voltage gain is now going to be given by minus GM1 into this effective output resistance. So what you see here again is that if you look at this, even though R down is going to be very large because of the cascade effect, because R up is restricted only to RO3 and in a parallel convention, the smaller transistor prevails, you see that the output resistance of such a stage remains close to RO3 rather than take into effect the cascade. So in this case, what's happening is even though you have connected a cascade configuration at the bottom, because your load is not large enough or your load connected on top is not high enough, it's not able to support the gain. So this configuration, if you look at its small signal gain, it looks very similar to GM1 RO3 or RO1. It's going to be very similar to a single stage common source, right? And that is because when you connect the cascade stage, it automatically brings a larger R out. And so you have to ensure that you're able to support this larger output resistance when you connect the current source. So this therefore leads us to what are known as cascade current sources. That is, if you want to take the full advantage of the cascade and get the larger gain, you need to ensure that the load that is connected to your cascade is also one with a very large resistance so that you can make the same output resistance and hence get a large gain from the circuit. So here again you see that this M4 M3 combination is essentially a PMOS cascade current source with a very high output resistance of RO4, and you're looking at RO4 through GM3 RO3, so it becomes GM3 RO3 RO4. So if you look up, it's going to be GM3 RO3 RO4. Looking down, it's going to be GM2 RO2 into RO1. Effective transconductance at the output node is just going to be given by M1, which is GM1. And so therefore the gain of the circuit is going to be minus GM1 into GM2 RO2 RO1 parallel GM3 RO3 RO4. So what you see here is that by connecting a better current source or by connecting a current source with a larger signal resistance, you're able to extract the effective current voltage gain of the cascade. So the cascade gain, to utilize the cascade gain, it is important that you understand what the load is and make sure you connect the right load if you want to gain the full advantage of the cascade. Thank you.